Alright, so in this video, we are going to look at an overview of a course that I'm creating called Rooting Theory. Now, rooting theory is the theory of movement. Right, so really, it's just about moving around, right? Just moving like this. That's really all it is. It's the theory of movement. Okay, so then, really, when I say to move, I really mean to root. And also, we call an object that moves a rooter. So now, I would like to talk about the table of contents. There are 8 main chapters that we're going to talk about, and chapters 9 plus are going to be more advanced topics. But before we get into the table of contents, we need to discuss one thing, and that is, what is a curve? For our purposes, we are going to think of a curve as an object that a rooter can move along, or trace out. For example, you can think of my marker as a rooter, right? As my marker moves, it traces out a curve. So this would be an example. Or we can think of an object moving along the curve, right? That's really all a curve is, right? As another example of a curve, my marker can trace out, say, a curve that looks like this. As you can see, we have what appears to be 2 different curves, right? They clearly look different. How do we distinguish between them? We're going to be looking at that in some of the first few chapters, right? These curves look pretty simple. We call curves that look like a snake a path. Curves that look like a ring, we call a cycle. Any other curve, it turns out, is just going to be way more complicated than these. So maybe something that looks like this, right? Way more complicated, right? So yeah, this is basically what a curve is, right? So notice I was able to trace out this curve, right, by treating my marker as a rooter. So that's the reason why it's a curve. But another way we can think about it is we can say that we have an object called a rooter that moves along the curve. And so that's what makes it a curve, right? So these are visual examples of what a curve is. It's basically just a scribble, right? Something that you can draw out. We're going to get into more detail about what a curve is in the first few chapters, but visually speaking, that's really all they are. So now we're going to start talking about the table of contents of rooting theory. We start with chapters 1 through 4. Chapters 1 through 4 are all about the properties of curves. More specifically, starting with chapter 1, we literally spent all of our time in chapter 1 trying to define what a curve is, right? We spent all of our time doing that. It's like, oh, what is a curve? What is it, right? That was good. In chapter 2, we look at a few of the basic properties that curves have. And what I mean by basic, you're going to see when we talk about it in chapter 2, because according to some people, some properties may be considered basic, while to some others, other properties may be considered basic, right? You'll see what I talk about when we get to chapter 2, right? It'll be pretty interesting. As for chapter 3, we talk about what are called partial curves. Now that sounds scary, right? Oh, that was good, right? But all a partial curve is a part of a curve, right? So for instance, if I have this curve, if we want to look at a partial curve of this curve, then for instance, what I've highlighted in black right here would be an example of a partial curve of this curve, right? As you can see, every single point on this partial curve is a part of the whole curve, but if we were to redraw out this highlighted portion, right? So I've redrawn this highlighted portion right here. On its own, it appears to form a curve, right? It's a curve itself. And so really, it's a portion of a curve where treated on its own, it also resembles a curve, right? And so that's really all it is. We're taking some portion of a curve and we're looking at properties of them, right? Properties of partial curves. Another thing we spend a lot of our time doing in chapter 3 is we talk about what happens if we remove a point from a curve. For instance, if I take this point right here and I remove it from the curve, I still have a curve. Turns out that on any curve, there may be some points that we can remove and the result is still a curve. And maybe there are some points we can't remove at all. For instance, let's say our curve had something that looks like this. Basically, this looks like a balloon, right? You can think of this like it looks like a balloon. Well, if I take this point right here, where the balloon connects to the curve, if I take this point, it turns out if I remove it, the resultant is no longer a curve because the balloon is now disconnected from everything else. The reason why it's no longer a curve is because if I have a rooter on the balloon portion, it can no longer reach anywhere over here. So these points all together don't form a curve because if I'm a rooter, I can't reach any point over here. Chapter 4 is all about cycles. We basically spend majority of our time in chapter 4 talking about what happens when a curve has a cycle or doesn't have a cycle. For instance, if we look at this curve, it turns out every point on this curve is part of some cycle. For instance, this point is part of this cycle. This point is part of this cycle. This point is, well, part of quite a few cycles actually, right? Part of this cycle. Turns out every point on this curve is part of a cycle. Okay, so then what properties do such curves have, right? That's sort of what we look at, right? And also, here's what a curve that doesn't have a cycle looks like. As you can see, no point on this curve is part of a cycle. There is not a single loop of points in this curve. Clearly, right, they look completely different from each other. What properties do these types of curves have? That's what we spend majority of our time in chapter 4 looking at. In chapter 4, we also talk about some more special properties of removability of points, right? Which it sort of builds off of what we talked about in chapter 3, right? But that's basically it for chapters 1 through 4, properties of curves. But when we get to chapters 5 through 6, this is where we really start talking about rooting, right? We really start talking about what happens when we move along curves. That's chapters 5 through 6. More specifically, in chapter 5, we talk about roots. For now, we can think of a root simply as movement along a curve, right? Just moving along a curve, right? We'll talk more about what that means in more detail starting in chapter 1 and definitely more in detail chapter 5. In chapter 6, we talk about something actually quite interesting. We talk about rooting as a language. It's really interesting because it turns out we can translate movement along a curve into a language, which is, that's pretty creative and it's pretty interesting. And that's really what we spend a lot of our time talking in chapter 6 about, right? It's all about trying to write movement along a curve into a language, which is that's pretty deep, right? It's like how is language rooting? Language is words, right? That was good. How is it movement along a curve? Language is words, right? I want you to remember you thought that. That was good, right? But yeah, that's chapters 5 through 6. It's all about movement along a curve. As for chapters 7 and 8, let me move back up to the top. All right, table of contents continued. Chapter 7 is all about rooting spaces. What's a rooting space? A rooting space is a space where a rooter can move around it, right? So for instance, this could be a rooting space. The basic idea of a rooting space is we have some rooter in the space, and the rooter can move around to any location it wants inside the rooting space, right? That's what it means for it to be a rooting space, right? You can move around in it. But you can't move outside of the rooting space. This is not allowed because anywhere outside a rooting space is what we call a wall space, right? It's a wall, right? You can't move into a wall. Oh, can't do that, right? No, good, right? You have to remain in the rooting space, right? So everywhere in the rooting space is the rooting space, but everywhere outside of it is what we call a wall space, right? And this is what we call the boundary between the rooting space and the wall space, right? We look at properties of rooting spaces when we get to chapter 7. So now that we've talked about that, that's chapter 7, rooting spaces. Chapter 8 is all about rooting in time, right? Chapters 1 through 7 is all about moving. We never care about how fast we move until we get to chapter 8. What is, the relationship between movement and time, right? We talk about concepts like position, velocity, and acceleration, something that you would typically see in physics, right? So it's not super advanced, but we get a little bit of taste into it. Just so you guys know, position is just your location. I like that, your location. That was good. Velocity is rate of change in your position. Acceleration is rate of change in your velocity. What's after acceleration is what we call jerk, which is rate of change in your acceleration, but we don't care about that. We only care about these three because it's easier to deal with, hopefully, right? Yeah, chapter 8 is all about rooting, but bringing time into the picture. Everything after chapter 8 is going to be chapter 9 plus, where we're going to look at more advanced topics, right? That is building off of what we talked about in chapters 1 through 8, and, going into more detail. Right? One example of an advanced topic could be shortest distance to travel from one place to another. For instance, suppose you're at home and you want to go to the grocery store, right? Clearly, there are many different ways. For instance, I could just do that, or I could do some weird convoluted path like that. There are many different ways to go from the house to the store, but what's the quickest way, right? An advanced topic would be shortest distance. Another advanced topic we could talk about is something called outrouting and tracking. This is actually a topic I want to get to because it's actually really interesting. So really, there are two different types of routers in this case, outrouters and trackers. An outrouter is a router that wants to head away from other routers, while a tracker is a router that wants to head towards other routers and try and catch up to them. So this is the table of contents. The last thing I would like to talk about is the course objectives. Okay, so this is basically you asking yourself, okay, what do I get out of this course, right? What do I get out of it, right? Well, there's 4 things. Sorry, not much, right? That was good. But the first thing is, well, the ability to think critically about the concept of movement, right? There's really 4 main ideas we're talking about: curves, roots, rooting spaces, and rooting in time, right? All trying to tie these 4 things together into the theory of movement, right? To the ability to think critically about those 4 ideas. Now, the second objective is to be able to think about examples and how they relate to general principles, right? After all, this is a theory course. We're going to be thinking about the more general principles behind what we're talking about. How do we actually know that the general principles themselves are correct? Well, we need to be able to find a way to reason about them. The ability to construct some sort of argument that says, well, those general principles are correct, right? In this course, we're going to gain a basic understanding of the language of how we come up with an argument proving these general principles. A basic understanding of the language of proofs and logic, right? Oh, I probably just weeded out about half of you right there. Well, see you guys later, right? That was good. We aren't going to be doing super formal proofs, but the ability to come up with a logical argument for whatever you're claiming is important, right? You need to be able to argue why what you're saying is true. For instance, consider any curve that is itself a single cycle, right? This is, if you recall, this is what we talked about when we introduced a curve. It's exactly one cycle. It turns out I can take any point on the curve and remove it. The resultant curve is a path. It's a path, right? As you can see, it's a snake of points, right? If I add that point back to a cycle. Say I take this point and I remove it. We have a path, right? It's a snake of points. Turns out it doesn't matter what point I remove. I can remove any point from my ring. I get a snake. But why? How do we know that that's actually what happens? Well, we come up with a logical argument for why that's true. And so we're going to learn how to construct arguments like that, right? To gain a basic understanding of it. In this course, we are not going to be looking at super formal proofs. If you want to look at formal proofs of what we talk about in this course, I recommend actually looking into another course called graph theory. Much of the stuff we're going to be talking about is part of a course called graph theory. We do change some of the wording a little bit, but it is what it is, right? When I was first thinking about this sort of stuff, I actually didn't know anything about graph theory, but much of the stuff we talk about is actually related to graph theory. So if you're interested in more stuff related to this, I recommend looking into graph theory. But yeah, that's it, right? We aren't going to be looking at super formal proofs. It's all about the ability to come up with a logical argument for whatever you suspect is true. As for number 4, not only the ability to come up with proofs of general principles, but to be able to ask yourself, is this true? The ability to come up with conjectures and to test them. A conjecture is a statement that might be true or false, right? It's one or the other. We don't know whether or not it's true or false. As an example, a conjecture could be, suppose I have any curve where every point on the curve is part of a cycle. The conjecture is, no matter what point I have on the curve, if I remove that point, the resultant is still a curve. That would be a conjecture. We don't know if it's true or false, but it's one or the other. For instance, well, let's see. If I take this point, yeah, everything is still connected together, right? It's still a curve. Okay, this should be the same if I take this point, and yeah, still a curve. If I take this point, turns out, yeah, everything is still connected together. We still have a curve. It turns out that in this curve, yes, I can remove any point on the curve, and the resultant curve that I get from that is still a curve. Everything will still be connected together. But it turns out that the conjecture that I said is not true for every curve, where every point on the curve is part of a cycle. For instance, let me show you guys another curve where every point on the curve is part of a cycle. The infinity curve, right? Let's go! Every point on the curve is part of a cycle, right? This point is part of a cycle. This point is part of a cycle. This point, also part of a cycle. Every point on the curve is part of a cycle. The conjecture was, take any point on the curve. If I remove it, the resultant curve is still a curve. Well, indeed, if I take this point, yes, if I remove it, we still have a curve, right? As you see, it's still all connected together, right? Same thing over here. If I take this point and I remove it, the result is still a curve. It shouldn't matter what point I remove. That's what the conjecture said. But if I remove this point, now we have two disconnected pieces. So it's no longer a curve. So the conjecture that I came up with is false. And so that's the idea of principle number 4, or objective number 4. The ability to come up with conjectures and to test them. And so, yeah, that's pretty much it for the course objectives. And that is all I would like to talk about in this video, right? So yeah, this is basically an overview of what we're going to be talking about in this course called rooting theory. Anyways, yeah, that's pretty much it for this overview.